This one is 2.11. In this, there's a square reinforced concrete pier, which is 0.3 by 0.3 meters in cross section, and the height here is 1.2 meters. And this is loaded under compression, so there's a load 670 kilonewton on the top. And this is a concrete pier which is reinforced with 8 vertical bars, and their cross section is 25 by 25 millimeters. So if you look at from the top here, this is the concrete pier. So this is 0.3 meters, this is 0.3 meters. So here there are this 1 2 3 4 1 2 3 4 total 8 such members are there. Now for the concrete, your elastic modulus is given here, and for these steel bars the elastic modulus will be 205 gigapascals. We need to figure out the stress in the steel and the concrete, and we need to find out the deflection. Okay, so what we can do here is we can look at this cover plate and draw the free body diagram for the cover plate. So on this one there is this 670 kilonewton coming from the top, which will be balanced by these two forces. One is coming from the concrete and the second one is coming from the steel bars. Now from the force balance here, we can write down your FC plus FB need to be 670 kilonewtons. Now there is only one equation and we have two unknowns here. So the second equation will be coming from the geometrical compatibility. So that is basically the deformation in both of these concrete as well as your bar should be exactly same. So the deformation can be written with the help of Hooke's law. So force in this member times length divided by elastic modulus and area, and this is going to be valid for both the concrete as well as your steel bars. Now length is same for both of them, so we can cancel out. So we can have a relationship for your FB in terms of FC as AB EB divided by AC EC. Now the elastic modulus is known for both of them. Now let's look at the area there. So going back to this figure on the top that I have drawn, the total cross section area is 0.3 into 0.3 meters square, and this is coming from both concrete as well as your 8 bars that we have, right? So if you look at your concrete area and we substitute the bars area there, which is 25 times 25 millimeter square, from this we can find, this is basically 0.09 meter square. From this we can find that your area for your bars is only 0.005 meter square and area for concrete is 0.085 meter square. So now we have this equation 1, equation 2, substitute the value of EB, which is made of steel, as 205 gigapascals, and for the concrete it is given as 17 giganewton meter square or gigapascals. We can substitute these numbers in equation number 2 and solve for the value of FC and FB. So your FC comes out to be roughly 392 kilonewtons and your FB comes out as 278 kilonewtons. Now for stresses, that's the next thing that is asked in the question, which will be your FC divided by AC. Similarly, your sigma B is going to be FB divided by AB. So your stress in concrete is 4.6 megapascals, and in your steel bars it is 55.6 megapascals. Now for the deformation, we can use any one of these relationships, either this one or this one, and substitute all these numbers. So delta C equals to delta B comes out as 0.3255 millimeters. So in this problem, internally at the end we can see that this 670 kilonewton force that was coming from the top, it was balanced by the concrete force and your FB force, which is basically 8 times individual member forces. So there were total 8 reinforcing bars there, so this total force will be equally divided. So where is that force? This will be equally divided. So each one of them will be taking 278 divided by 8, and since area is the total area that I have taken, stress is not going to change. Stress is going to be same. Force is divided, area is also divided, so stress is going to come out as same there. And from the deformation perspective, all of these bars which are sitting right next to each other in this manner, all of these will be moving by the same amount, so delta is also going to be same in all these individual bars.